Hello everyone, and welcome to this 10th lecture of the digital image processing of remote sensing data course. We have reached to almost midway of this course. In the previous lecture, I have discussed the image enhancement techniques part 1, in which we have discussed how radiometric corrections and atmospheric corrections can be performed. Also, we have discussed linear contrast stretching, some of the techniques of linear contrast stretching. Now let's go for nonlinear contrast enhancement, where the input and output data values do not follow the linear relationship. In case of linear contrast stretching, this is not true, where it has to follow the linear relationship. Input and output values are related by transformation function, which is by equal to function fx, and increases or decreases contrast in different regions of histogram. So depending on the requirements, we may go for this one, and that is there are various ways of involving, that is mathematical, logarithmic, inverse log, exponential, square root, cube root, and there are nonlinear contrast stretch also based on statistical. Most popular one is the histogram equalization, maybe Gaussian stretch, and trigonometrical also, very rare to perform, but it is available, the arc tangent. Gamma stretch, gamma refers to the degree of contrast between the mid-level gray values of an image, and gamma does not alter the black or white values or affect the white values in an image, only the mid values. And by applying a gamma correction, because this is non-linear stretch, so it need not to follow the linear relationship. So if we apply this gamma correction, we can control the overall brightness of a raster data set. And very soon we would be seeing some examples of these stretches. Further, the gamma changes not only the brightness but also ratios of red to green to blue of different bands which are being represented in our remote sensing data. Gamma stretch values less than 1 decrease the contrast in darker areas and increase the contrast in the lighter areas. And this darkens the image without saturating the dark or light areas of the image. In linear contrast stretch, this was a problem. So here 3 images are shown, the same image with different gamma stretch. The first one without any stretch, the second one the original with 0.5 gamma, and then you are having the original image with 1.5 gamma, and you can compare the quality of image. Like point gamma is has become very dark, but whereas if we go for higher gamma, then we can have a much better contrast in the image. Similarly, there is one image which is suffering because of low contrast. If we bring if we see, say this is the example which I have taken from ArcGIS, and if you see that we are not using any type of stretch, the type is none is mentioned here, and when we go for histogram, then the distribution of histogram in a very limited range. Instead of occupying the full range which is available between 0 to 255, it is occupying a very small range. Minimum value and maximum values are also mentioned. Maximum values are only little bit are there, but minimum values is just 41. So most of the data is distributed between 41 to maybe 80 or 90, and that is why this image is suffering for a very poor contrast. So our aim should be to improve the contrast, and if we go for this gamma stretch image, this is how we have chosen here the stretch accordingly, and the quality of image has improved, as well as the distribution of the data after the stretch can also be seen here. So now instead of occupying or starting our minimum value at 41, now we are having at 26, and the maximum value of course 255 which is there. So on the right side of the histogram, because values were already there, so no changes, but the contrast has improved on the lower side of the image or the pixel values. And the next one is the logarithmic contrast stretch, which is again nonlinear contrast stretch. In this process, the logarithmic values of input data are linearly stretched to get the desired output values. And it is a two-step process. In the first step, we find out the log values of the input pixel values, and then in second step, log values are linearly stretched to fill the complete range, which is between 0 to 255 in case of 8-bit image. Generally, the image processing systems which we are using based on the 8-bit image processing system. Logarithmic stretch has greatest impact on brightness values which are found in the darker part of the histogram and on the low DN values. And generally the distortions are coming mainly on this side. Here the example of both nonlinear and linear contrast stretch is given that logarithmic will come on this side, and whereas inverse log will come like this. And this is how this is the sort of LUT. These are the brightness values, input brightness values. These are the output brightness values. If we go for different types of stretch, like instead of linear, we go for nonlinear, then we can go for this kind of shape, or piecewise and linear contrast stretch is also possible. So input values are between this range and output are coming generally between 0 to 255. Another very popular one, contrast stretching, which is nonlinear in category is histogram equalization, and this is based on the basically the frequency of pixels. So in this technique, the histogram of original image is redistributed to produce a uniform population density. As I mentioned, that the bars you can take or you can think like this: the bars which are original histograms are having a small height will be redistributed in a manner so they all bars having the same height, and that is why it is called histogram equalization. So this is obtained by grouping certain adjacent gray values, and thus the number of gray values in the enhanced image is less than the number of gray levels or values in the original image, and contrast is increased at the most populated range of the brightness values. So wherever the most of the values are there, pixel values are in a histogram, and there the contrast would be the maximum, and that is the real target actually. The tail end, if we improve the contrast of the tail values, then it doesn't improve the contrast of the image much. But if we improve the contrast of the where the maximum values or the highest frequency pixel values are present, then definitely contrast is going to improve. We will see the example through the images as well. So it automatically reduces the contrast at the both ends, that in very light or dark parts of the image associated with the tails of a normally distributed histogram. And in histogram equalization, the gray values are assigned to display levels on the basis of their frequency of occurrence, and image analyst must be aware that while histogram equalization often provides an image with the most contrast of any enhancement technique, it may hide much needed information. So whenever one is going for this kind of enhancement, one should take care that it is improving sometimes too much contrast within the image. And if you are going making interpretation based on histogram equalized contrast stretch, one has to be careful. And this technique groups pixels that are very dark or very bright into very few gray scales, and if one is trying to bring out information about data in the terrain shadows or there are clouds in your data, then histogram equalization should not be applied. This is the example of histogram equalization, that here the data is distributed like this. When histogram equalization is performed, these high frequency values where the maximum values were there have been redistributed like this, and image contrast has improved very significantly. Similarly here, one more example here. This is the original image and this is the original histogram of the image, but once it is histogram equalized stretch is performed, then this is how the distribution in the histogram. So it occupies almost full range, but the mid-range values are stretched maximum where you are having high frequency of the data. Here also one example is through this ArcGIS is that this is the distribution of the data through histogram, and in histogram equalized image this is what. So as you can visualize here while comparing original image with histogram equalized image, that you are having very high contrast. Sometimes for a better image interpretations one do not need very high contrast, so one can avoid for that in that case, but otherwise it is a very good technique. The original histogram and the redistributed histogram through after the histogram equalized stretch is both are shown together here, which you can realize that how this has been redistributed. Here also the histogram equalized option in ArcGIS has been chosen and the image has been enhanced. There is a percentage cut of a stretch, and so that you cut that this much data I don't need on the tail values, and then in between the values are stretched. So the percentage linear contrast stretch is similar to the minimum maximum linear contrast stretch, which is most common, except this method uses a specified minimum and maximum values. User will define or decide which are the minimum values or maximum values rather than the original minimum and maximum values of the image. There is you can also involve the statistical data or techniques. So like standard deviation, contrast stretch or linear stretch can also be performed, which is more or less similar to minimum maximum linear stretch, except this method uses a specified minimum and maximum value that lie outside a certain standard deviation of pixels from the mean of the histogram. And the standard deviation from mean is often used to push the tails of the histogram or values, low and high pixel values, beyond the original minimum and maximum value. So like in a Gaussian distribution, in a schematic it is shown that one standard deviation and then 2 standard deviation, 3 standard deviation, how. So in a normal distribution about 68% of the values are within 1 standard deviation of mean, and about 90% are within the 2 standard deviation, as one can see. So that there only 5% of the data remains in the tail. So areas once we do not take that much area. So areas under normal curves for various standard deviations from the mean are shown here, which we can see that in when we go for 2 standard deviation, roughly only 5% or less than 5% areas is left. So here the LUTs for different like in histogram of low contrast image, when we go for this, then this is how LUT will look, and the minimum and maximum values are stretched here. So this is the minimum maximum contrast stretch. When we go for this standard deviation, 1 standard deviation contrast stretch, so 1 standard deviation will involve about 68% of the values. This is the LUT of the same, and this is how the distribution of the values in a histogram will look. Now we see in case of real images, this is the original image and the corresponding histogram, which you can see not much distribution is there, and therefore image is completely dark. Hardly one can make any kind of interpretations except can see 2 major areas. But in a simple minimum maximum stretch we can do that performance, but it maximum values goes up to say 140 or 50, and therefore you do not have even much contrast as one would like to have. If I go for 1 standard deviation, then now I am occupying the entire range which is available for us between 0 to 255, and the contrast of this satellite image improves very significantly. So original image, one more example here, the same image which we have been taken in previous examples in case of gamma stretch and other stretch, is that this is the original image. Originally image is not that bad, but if we go for standard deviation stretch, it improves further. Very significant improvement has been made in this image, and after this standard deviation stretch and our interpretation will definitely improve. This is how the distribution of histograms, both original, which is in darker or black area, and then the stretch one is also shown. And in the example of ArcGIS, this is what you would choose standard deviation, and this we are going for 2.5 kind of thing. So this brings to the end of this enhancement part, which is the second part of digital image processing technique. Thank you very much.